we fixed it and fixed the instructions and so on. So that's good. If you could do that next time, that would be nice. Because if everyone tries to do the assignment in the morning of the submission, then we can't do that. If some people will try it and then they see, oh, this doesn't work, and then we can fix it in time for everyone else, that's better. All right. Can someone try to dim these lights? It's over there. Just give it a shot. Give it a shot. Likely less complicated than what we're going to be talking about. Okay. So last time we were talking about detecting key points, detecting, some people call them corners. No. Okay. All right. This is just so you guys can see the projection better. So we're talking about how to detect corners and key points. So we're talking about the Harris operator, how to use different convolutions to efficiently find corners in the image. So we will keep talking about that using some similar methods. And then we will go and talk a little bit about how to create descriptors for these points, because the goal that we set to ourselves is to be able to find the same key point in two images. So we want to be able to look at key points in one image, look at key points in another image, and do a matching between them. Right? For that, so we can find key points. We already saw how to find the key points in one image, but now we're thinking about matching. And this is where the descriptors come into play. So every key point will get a descriptor, and the descriptor will basically tell us how to match it to another key point. So we look at some nice descriptors for feature points, and then we'll talk a little bit about the matching, and we'll keep talking about it in the next class too. All right, so multi-scale feature detection. So you see I have many scales. That is the multi-scale feature detection. All right, so last time we talked about Harris, how to extract key points. And it was not scale invariant. So we looked at an image, and we extracted the key points at the pixel level. We did one convolution, another convolution, took a gradient here, a gradient there, second derivative, and so on. And we came up with, where the corners are, basically. Some corners in the image. But if our target image, if there was any kind of transformation in our target image, let's say it was downscaled by half, we would no longer be able to find the same points because it's not invariant to scale, right? We were only looking at one scale. So here, what I wanted to point out is that some key points will appear and some will disappear. So you see how the elbow, for example, does not appear in scale 1, but it does in scale 2, in scale 3, and scale 4. And some other things that were in scale 1 sort of disappeared in scale 2 and scale 4. So it's not invariant to scale. So we need to figure that out, how to do that. All right, so what we could do is we can use an image pyramid. So we saw the pyramids. You also had to construct one of those pyramids for your assignment, right? A Gaussian pyramid where you blur and downsample. So if it's low pass, downsample, and low pass and downsample, or low pass and downsample, so that you basically guarantee there will be no aliasing. But now we have, a multi-scale representation of the image, and we can do the same sort of Harris corner detector at each one of those scales, and basically pick all of the points that we find in all of the scales, and these will be the key points that we have. So some will be smaller key points. We attach a scale basically to every key point. Key points can be small, bigger, bigger and bigger and bigger, until we have like very large key points. But that's how we can do that. So how do we pick the scale for a key point? This is the Harris operator. I just did a for loop. Harris operator over a scale of about 1 to 20, going down in size. Right? This, over there on the left is the original image. This is the original downsampled by a factor of 20. Right? And I just ran this to the Harris operator. So you see how some key points, they always repeat throughout that. So we don't want to take, let's say we did that, maybe we did it for 5 scales. We don't want to take the same key point with different scales. We want to set what is the best scale for that particular key point, like the elbow of the guy, right? We want to have one key point there, but we want to say what is the size of that key point, right? We want it to be scale invariant. So we have a key point in the elbow, we have another image that's smaller with another elbow. Now the key point is smaller. You want to be able to match them. So we could use the Harris response, the Harris operator response, to do an automatic scale, finding automatically the scale using those responses. We basically plot this. Right, this is what I came up with. You plot the response, and you pick the highest peak on that response, right? So there are other responses that we could use to find different scales. Harris is just one of them. People came up with a lot of different things, and we'll touch on a wide variety of things. But I want to tell you about a couple of interesting ones. One is called the Laplacian of Gaussian. So the Laplacian of the Gaussian is basically a Gaussian that we took its second derivative, the Laplacian, the Laplace operator, right? So you can think of it as blurring the image and taking the second derivative, right? So in a Harris operator, we had to take some gradients here, against there. We did the autocorrelation matrix. I don't know if you guys remember. We did the autocorrelation matrix, put it there, we took the eigenvalues. It took forever. So it's a slow process. That's why not too many people would use it. But the Laplacian of Gaussian can be represented as a kernel, and we can just do a convolution. Now, it also gives us control over the size of the Gaussian, the size of the Laplacian, right? We can determine different sigmas, and we can do detection in scale. So we take the same image, and we just do multiple convolutions, right? We take the same image, and we just apply it to different, this is another for loop that I did, just varying the sigma, right? The same image, I applied the log, the log, the Laplacian of Gaussian, the log operator, at different scales. And now, what can we take for key points here? There's already a hint. What do we do for key points? Let's say that we did this convolution. What are the key points? What are the important points? is written on the slide. So this is blurred, so we already destroyed most of our high frequencies. What's this? What's this on the slide that I wrote as a hint? Right, you take the maximum values and the minimum values, right? You take this, and this is another. All of these things. These are important points. These are the areas that maximize the response. To this. Let me see 1 second. It's here. Excuse me one moment. I want to see if I have it here in the slides. If I don't, I'll draw it on the board. No, I don't. Okay. Let's do that then. Let's do that. Right. So we have our kernel, which we use for the convolution, right? And we're looking for the minimal and maximal point. So let's say we have an image that looks like this. It's all zeros except for a little block of ones, right? 1 and 0. A little block of ones. It's all 0 until we hit some ones and we go back to 0. Okay? In convolution, basically what we do, so you remember, we basically take the kernel and we apply it for every point in the image. So all the zeros are going to be zeros, but so our kernel looks something like this, right? Deeper here. Like that. The kernel looks something like that. And we apply it to that sharp edge. What is our goal here by applying this? We're looking for key points, we're looking for corners, we're looking for things that are distinct. This is just 1D, but in 2D you would look for things that are corners, are key features, important features that will describe the image, will be unique as well. We'll get to that in a second. Right? So we apply the convolution. See here. And basically, the beauty about this thing is that if you line up the size of your feature with the size, with this sort of the size of your log using the sigma parameter, you will get a very good response. You will get like a peak in here, right? Just like these peaks. We did a convolution, it's like a 2D convolution, right? Where we take the peaks and the valleys, because these things basically, peaks translate like that, and valleys are the same. Have ones, and then a little well of zeros will translate to a minimum. Right? So we can take the peaks, the minimas, and the maximas is our interest points, right? So we take these, and we do what we call non-maximal suppression. We basically look for just the maximum ones. We do it at scale. We vary the sigma of these things. We get bigger ones, smaller ones, so we can detect different kinds of features, different kinds of scaled features. A bigger table here like that will need a bigger Gaussian, and we'll have a big response, and a smaller one will have a small one, and so on. Right? Well, we just pick the maximas and the minimas as our key points. This is an actual, I just ran this algorithm on this image, OpenCV, Python, and that's the result. You get some of the features are very small, some of them are medium, some of them are larger. So you can see how, it's called a blob detector, we can see how it corresponds. So let's do that again. Right. So you see how it corresponds with different sized blobs. For example, the hand here, you can sort of think of it as a blob. Imagine you blurred this image pretty significantly. This is sort of a blob, so it picks up on that. Here, there's sort of like a little area that it likes. All right? Okay. But this is again kind of slow. We have to either take the same image at the original resolution and do a full convolution over it with different kinds of sigmas, right? A convolution is a pretty intensive, computationally intensive operation, right? You have to go through every pixel, and for every pixel, you're going in a window, a pretty big window, especially if you're going up in those sigmas, right? You may be even looking at a window of 30 pixels by 30 pixels for every pixel in the image. That could take a very long time. So what we could do is do a little trick. We can take the difference of Gaussians. Imagine you have a big Gaussian and you subtracted a smaller Gaussian. Right? It's very simple. I don't have the board again, but you take a regular Gaussian with a bigger sigma and you subtract a Gaussian with a smaller sigma, and you get something like this. It looks very, very similar to the Laplacian of Gaussian. It's basically like a blob detector, a corner detector, like we saw. If we have a feature that goes up and down like that, if you have the right sigma, it will pick up on it with very high response, right? So now we can take the image pyramid, and basically the image pyramid is applying a Gaussian. After you take an image, you apply a Gaussian, blur it, and you downsample it. You blur it and you downsample, and you blur and downsample, right? This is what I did here. OpenCV, peer down. You used it in your homework. OpenCV, peer down a few times. And then you take the high level minus the lower level that has a bigger Gaussian, and you end up with the dog, the difference of Gaussians. That's it. You just do this minus that. You do a pyramid, this minus that. This minus that is arguably... Sorry? That's good. This is a difference of Gaussians, two Gaussians, a bigger Gaussian minus a smaller Gaussian, and it approximates the Laplacian of Gaussians. It approximates. It's a very good approximation. I tried to line up the log with the dog, and I couldn't, so I then piplot and just they didn't line up. So that's why I'm not showing the log here. But it's a very, very similar function, and this can be done much more efficiently. You just do a Gaussian pyramid and do this minus that, and you look for the maximum the maxima, right? The same as we did before. It looks for the maximal and minimal points in those. And then we have it at scale. Then we can get a lot of key points in different scales, right? Some other tricks that people do. So this pyramid thing is very important. A lot of these key point detectors use image pyramids, all right? Because it allows you to work in multiple scales. Okay. The fast key point extractor is fast. It's a fast key point extractor. The idea now that instead of working with convolutions, we work at a pixel level. We look at pixels surrounding our candidate key point, and we look for things that look like corners. So what are corners? Like we said, last time we said, if you go around your certain pixel in any kind of direction, if you find a change in that direction, in all directions, or most of the directions, you're at a corner, right? If you're standing at a black pixel and you go to the right, to the left, up, sideways, right, diagonally, and everything is white, then you're at a corner, right? If you're black and everything is white, right? So that's the idea about the fast. You just go in around your certain pixel, or your center pixel, and you look for things that are either darker or brighter. If you find that everything is, or most of the things are darker, it's a corner, or the brighter than center value. Okay? But this is not even fast enough. So they said, all right, so we don't have to look in all, 16 sort of pixels around our pixel. We'll just look at 2 pairs of them. We'll look at 1 and 9, and 5 and 13. Right? We'll just check these 2. If they don't pass this test, we keep going. Right? Okay, but this is sort of arbitrary. 1 and 9, 5 and 13. So it said, why don't we use machine learning? We learn what is the order and which are the pairs that we should check so that we are the fastest. And they built a decision tree. I don't know if you guys know about decision trees. Probably most of you know about them. But the idea is that you just make a decision towards finding your goal. Anyway, we'll get to that. We'll get decision trees later.
Yeah, you mean we check only, for example, 1 and 9 for the fast, right? To be more efficient.
Right. Yes.
If we use decision tree, it may be a little slower.
Right. The decision tree basically helps you to reject fast. You want to reject things that are not corners very fast. The decision tree is you go one decision, you do, okay, I'm going to check my certain value against 1 and 9, and then I'm going to check them against 5 and 13, and then I'm going to check them against 16 and 8, and then I'm going to do this, all of these different, it looks like a tree because you're taking right and left, and at point, each node of the tree, you're taking a different decision, right? The idea is to reject those corners as fast as we can. So that's what they did. They took a bunch of images, a lot of images, and they built they built a decision tree out of that, and that's how the fast detector came about. It's very fast.
What is the output variable for that decision tree?
Right. So a decision tree will tell you if this is a corner or not. It's a key point or not a key point. Right. Right. So we said how you are at the center pixel. And you want to know if this is a corner or not a corner. So you look around the center pixel. If most of the pixels are either brighter or darker than this pixel, then it's a corner, right? That makes logical sense, right? So how do you test if this is, how do you test how most of them, you can look at all of them, that will take a while, but you can look at just very particular positions, and you apply machine learning to know which ones and what is the order, the fastest order, right? So this is the fast key point extractor. It has a certain threshold, but as you can see, it finds those corner points, like the elbow and here and over there. It finds them pretty good. We've seen other kind of methods that are probably will take longer, because you have to do a convolution over all the pixels, and you have to look for maximum point and so on.
What is threshold?
Threshold? Oh, I'm missing an H there. Let's go. Threshold. Threshold. A threshold is, so it's a sort of very trivial thing. If you have a number and you want to know if it's above or below a certain threshold, then
Color intensity depends.
no. Oh, in the fast. So it's not exactly the intensity. So you're looking for things that are. Has to do with intensity. Look for things that are brighter or darker than your pixel. So you set a certain threshold on that. So let's say it's 20. So if this pixel in the middle is 100, you would look for things at either 120 and up to be brighter, or 80 and down to be darker. We consider them darker. And it's just a binary decision. Is it over or under that threshold? Threshold.
So how is this scale invariant, because we are doing it only for one resolution?
Right. No, we are in the implementation they use a pyramid. Just use a pyramid. And then they assigned, if a thing is considered a key point in that resolution, they just assigned that scale to that key point. They say this key point is in scale 6, right? Because in the pyramid we were at scale 6, and this key point has scale 3, right?
This image is for only one resolution, right?
This is for all the resolutions. Like I just use the default parameters for fast detection here. Right? Okay. So, and fast sort of revolutionized key point detection and a lot of algorithms, because it was actually feasible at real time on mobile phones. So, imagine 10 to 15 years ago, mobile phones weren't really as powerful. And so all those key point detection methods worked nice on computers where you had a lot of compute power, but on mobile phones really nothing could have worked. So they were really looking for very, very fast and efficient. And to this day, fast is one of the fastest, among the fastest feature detectors there is, even at scale and so on. Right? More key point detectors exist. There's virtually, I'd venture to say that there are dozens probably. Some of the more well-known ones are the MZER, the minimal stable external region, Agast, OFAST. OFAST is basically oriented fast. There's a fast key point, just a regular fast like we saw before with the circle around a certain pixel, center pixel, but with orientations from, I believe it's a Hessian matrix, but whatever. The determinant of the Hessian, so the Hessian matrix is basically just, it's very similar to the autocorrelation matrix that we saw with the derivatives, basically a matrix of second derivatives, and you take the determinant of that, and it gives you an idea if one pixel, if a thing is a key point or not, There's the good features to track by Shi and Tomasi, Daisy, Susan, Sensor. There's way too many. Way too many. And they all have their own, invariances and covariances, and they some of them are catered for very specific, like stereo. There's also things that are basically don't have rotation invariance, but since you're looking at a stereo image, for example, you're not expecting a lot of in-plane rotation variance. If you're looking at an image from two cameras that are basically oriented up, two cameras oriented up, looking at the same image, you would not expect one image to rotate 90 degrees, right? Because they're both looking at the same thing. So for stereo, for example, you don't need, rotation invariance. And so there's features that cater towards that. All right. Any questions so far on some things? Right. The decision tree, I don't know if I should go on to the discussions of decision trees now, but all right. Should we? I don't know. So, just to explain the fast idea, right? You have a pixel. Let's bring it up too. Nope. So you have a pixel with its surrounding pixels. And a certain pixel, a center pixel has a certain value, has a value 100. And around it you have pixels that are a little brighter sometimes, a little darker sometimes. And each of them give you sort of a decision. Is it over the threshold? Or is it under the threshold? Or the negative threshold? So you have your pixel value, and you want to see if it's over the pixel value plus the threshold, or is it under the pixel value minus the threshold? Right? So if you have a pixel here, you have sort of this accept region and reject region. Let's see the other way around actually. So if you are within this region, you're considered to be roughly the same color as that pixel. If you're outside the region, you're a different color, right? There'll be 1 if this, 1 if this, and 0 otherwise. This would be like a detection. For pixel P tag, a different pixel, you basically, if you are over the threshold or under the lower threshold, you're considered a different thing. Now, so these are just these binary decisions. There is RGB fast that you could use in RGB. Really, most of these detectors, they work on grayscale, but it's not really grayscale. They work on the luminance that we talked in a couple of weeks ago. We said how most of the information in the image is contained in the luminance of the image, the intensity, the color intensity. This is also how our eyes work. We can sense color, but most of the information is retained in the luminance. So some information is in the color, and there's some features that also look at color, at color in different when they're considering the scoring functions and so on, and the thresholds.
Because there are two regions that have different colors, but the
the same. Yeah, so you could do the same trick. You could just use it in the R and the G and the B channels, and then, all right, or a different color space. But it's the same idea.
Like if we use this kind of decision tree and train it over like thousands of images, we mean to say that there will be a specific sequence like 10, 14, 2, 3, 4, but it's constant for all the images, right?
Yes. So I didn't finish my point with the decision tree. So basically, you want to train or find a binary search tree. You want to do a binary search tree. So I guess everyone knows what a binary search tree is. I'm not going to explain it. You want to find the tree that will optimize over a certain function. A certain function is, in this case, we want to be able to classify whether it's a corner or not a corner, and we want to do it as fast as possible, right? So we want to keep the tree short, but basically we want to know if something is a corner or not a corner. And at every point here, you have your decision. So this would be the PI, and then we know another decision, PJ. Another decision. And in all the leaves what we have is basically sort of basically a probability. A probability that a certain pixel is the corner, right? So you want to make the least amount of these checks, because every check takes a little time. You have to take this, do this, minus that, see if it's over or under, basically do absolute value and look if it's over the threshold, right? So each one of the decisions takes a little bit of time. So you want to keep your tree as short as possible so you don't have to make as many decisions. If at this point, if this one decision with PI ended up true, then I know I have a corner to a very high probability. If it's a false, then I have to do another check, right? And if this one is true and this one is false, right? And this, the tree is not right? False, right? So we want to do the least amount of these checks because they take time, right? That's the idea with the decision tree.
So you have training data which says which pixels are and then you optimize those based on the tree.
Yes. When you're doing learning, you usually have supervised learning, you usually have training data. And so they took a lot of training data and they trained a tree, and then they take the tree, they basically unroll it in C code. If you look at fast implementation, you'll see a decision tree in C code. And that's how it's very, 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 very fast. We just use an image pyramid and we go at different scales. That's it. Anything about the logs and the dogs? We'll keep going and we'll get to that. All right. Okay. So, feature descriptors. So we know what are the interesting points in the image. We know what are the interest points. Usually things that are corners, things that have edges, are interesting because they will, they are sort of landmarks that we can find in another image of the same object, right? So we found those key points. We use the fast, we use the Harris, we use the logs, the dogs, blobs. We found interest points. Now, we want to know how to match them, how to get another image. We've also found key points there, and we know that the key points, there is some kind of matching between the key points. in those two images, but we need to find a way to match them. That's why we create a descriptor. A descriptor will describe this key point, will give it sort of an explanation, and then we can look in a different image to see if we can find a very similar key point. Right? So we create a descriptor. Usually those descriptors are vectors of numbers, and we can match them in a certain way. All right? So, why don't we just take a patch of pixels around each key point? Let's say we have the elbow, we found that in the shoulder, right? We found those as key points. Why don't we just take the pixels around them? And then we go to another image and we look for the same pixels in the other image. You just take a little patch of like 5 by 5 or 10 by 10, all the pixels around that point, and we look at another image and we look for a patch that is, roughly the same thing. We have other key points there. We just take this patch and that patch and we match them. Scaling, so there won't be invariant to scaling, because if you have another patch that's, that was taken from an image that twice as big, it just won't match. If you put this one on top of the other, you do this minus that, and it won't match. So scale.
Environment might be different. The way the image is captured in one image might not be exactly the same as how it is captured in another image.
Right, so there's some kind of variance. Rotation, someone said, true. So if you take one patch and you rotate it and you put it on another patch, on the same patch, also this minus that will not give you a very big, up to a point. If you rotate it a little bit, just a few degrees, it's okay. But any more than that, any more than a couple of degrees, it won't be okay anymore.
So intensities might be different. Even the information is same.
Intensity is different, right? Even if we take all the pixels, take this patch and take the same exact patch, we just take all the pixels and do plus 50 to their values like you did in your homework 0. You take this minus that, everything will be 50. You sum up all those 50s, it's a pretty big error. Even though it's the same patch, just a little, not a little, but a different in intensity. Even if you change it by 1, right? If your score between these two patches, take one patch, another patch, this minus that, absolute value, and sum up all those values, even if you change the intensity by 1 at every pixel, just instead of 100, do 101. Tiny change. According to our matching scheme with the absolute value, you come to a score of 100 between these two things. Right? Okay. You guys are right. It's not invariant to scale or rotation or intensity, which makes it a very bad descriptor, a very bad, useless descriptor. All right, so what can we do? Someone suggested we can still take a patch. Let's do this so you guys can see too. We can still take a patch of pixels. We just need to make sure that it's normalized with respect to scale, rotation, and intensity. Right? It's very easy. We have the scale and the rotation from our key point detector. Right? We do fast, we do Harris, we do whatever. We know the scale and we know the rotation to a degree. We unroll that rotation. Let's say we take a patch of pixel. We unroll that rotation. Right? So now we are axis aligned. We change the scale, so we always scale them down to 8 by 8. Right? And we normalize the intensity. Meaning that we do some similar thing to what you did in the histogram equalization. Right? We normalize the intensity. We see all the intensity will be between 0 and 1, and the mean will be in the middle. Right? This now is a pretty useful descriptor. It's a pretty useful descriptor. So we can do it in different scales, right? We just take those things, we unroll them, and we we match them together. That's a good idea, working with just pixel patches. But it has some disadvantages. It won't be that much invariant to things other than rotation. So rotation is okay, but usually in images, what we get is we get different transformations, like projective transformations, right? Where you change your perspective. Things basically, well, it's best to visualize, but things they don't just rotate. There's different transformations that go on with it, and also intensity. This is sort of suspicious.
Professor?
Yes.
How to choose this scale? How to choose these patches?
How to choose the scale?
Choose the patches.
Choose the patches. So we just saw a number of detectors, right? We saw right. These are corner detectors or blob detectors. It doesn't have to be corner. We saw some that are blob detectors, right? That would find things that are like round, kind of, right? Remember we saw that 3 minutes ago? We get those key points given to us by the detector. Now our point is to find a descriptor, is to find a way to say this key point looks like so. It has a vector of numbers that will describe it. Okay? So what are some things that we can think about that can give us some invariant properties? What are some things that we already saw that we could use to get some invariancy? Anyone?
You can use the frequency response.
Frequency response. We could. Right. Although that would not be rotation invariant, because that will definitely, if you change the rotation, you're basically changing the angles, right? You're changing the angles, and that determines, there's a frequency, but there's also the angle, right? In the Fourier transform. So it will be somewhat invariant, but not the rotation, for example. But it's a good idea. Easier things. I think we talked about this. Right. So in interest of time, how about we use some statistical information? Use a histogram. Let's say we take a histogram of just the pixel intensities in the image, or a little patch, just the pixel intensities of that little patch. If you rotate that same patch, the pixel intensities will not change. So it's completely invariant to rotation. Doesn't care about rotation at all. Right? Scaling. Let's say we take the same patch, we scale it down. We take the same histogram. What do you think will happen to the histogram? It will just scale down, right? Because we have less pixels at every bin. But it will scale down proportionally to the scale, pretty much, right? So if we normalize the histogram, we're not looking between 0 and 10,000, this is an actual histogram of that image, but between 0 and 10,000, we normalize it between 0 and 1, right? And then if we take another patch that we shifted the intensity up or down, we scaled it up or down, and normalize the histogram. Histograms are great, right? What if we change the intensity of the pixels? We take all the pixels, we do plus 50. What will happen then? The whole histogram will shift to the right, and then we are in trouble, right? What other invariant things that we saw that can give us pretty good invariancy? We could do some normalization, like we saw with the mops. We saw with the patches. We can normalize the intensity, and then do the same thing, right? True. What other things are invariant to intensity? Gradient. gradients are invariant to intensity because they don't care about the pixel value. They care about the change between the left pixels and with the left pixel and the right pixels. They take care about edges. So it's not about an absolute value. It's about a relative value. And so that is invariant to intensity. So intensity changes. So what do we do? We have histograms are good, gradients are good. Next step. A histogram of gradients. This is one of the most transformative ideas in computer vision that since sort of quote unquote was discovered, became huge in computer vision. Many different things are built on top of histograms of gradients. Feature descriptors are, sort of the front line of that. You can see many feature descriptors that are based on histogram of gradients because they are invariant to many things and they are easy to calculate, easy and fast to calculate, and so on. Right? So a histogram of gradient. We look at a certain patch, but instead of looking at the intensities, we look at the gradients in that patch, and we bin the things, right? We look at every point in that patch. We look at the orientation of the gradient in that patch, and we bin it based on that orientation. Our bins are basically over the angle of that gradient, right? Okay, so how do we get that angle and the magnitude of those gradients? Again, it's very easy. We do those edge-finding convolutions, just the first derivative, right? And we can approximate the angle, theta, there, by taking an inverse tangents because, I could do this on the board, but really, a tangent, is y over x over y, depends. And so your edge will tell you what is the change in x and what is the change in y. That's what these edge-finding convolutions do. They give you the first derivative in x and the first derivative in y. Will tell you what is the change in x and the change in y. That is the definition of a derivative. So if you do this minus this over that, and take the inverse of that, you get the angle, right? And the magnitude is the same way. You just imagine there's a little line there that goes, a certain way over the x and a certain way over the y. To find the length of that line, the magnitude of that line is just, an L2 norm, right? The distance of a line.
Professor?
Yes.
So the histogram is the histogram of those rows on the left.
It is a histogram. This is a histogram of all the angles here, right? So all of these little gradients, they have an angle.
And
This is like 15 degrees. This is minus 5 degrees.
Yeah.
So you basically sum that up. You sum up all those things, and you get an angle histogram. This is a very, 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 very important idea. A lot of things can be pre-calculated, like we calculate the first derivatives. We just calculate these things very easy. Histograms, very simple.
would this be unique for an image, or can you prove this by creating a similar image with a very similar?
Right. So it doesn't have to be unique. All of these things, and we'll get to that. There's ambiguity. There's ambiguity between these two things because it's impossible that you will only find just like this guy's elbow here, that will be only one place in the image that will look like that. I can already see how this down here where the jacket is already pretty similar to that one. So it's not unique.
I mean, the entire Instagram for an image, Instagram of grading and the angle.
Right. Yeah, we'll get to that. There's one descriptor called the HOG, the histogram of gradients, that does that for entire images. We'll see that in a second. Yes?
So you said that histogram doesn't solve the change in intensities problem, the normal histogram.
Yes.
So if we equalize the histogram to the whole range, 0 to 55, and then compare, then it would solve it.
Yeah, well, it's a little different. If you're just doing intensity plus 50, you're right, because if we take that, we shift it up, we stretch it back out, then you're right. But some intensity changes they usually don't follow all of the pixels plus 50. It's usually not that. It changes intensity. Plus, if you're doing, intensity plus 50, some of the pixels might actually go over to 55. But you can't save that information because you're constricted to those 8 bits you could use. So you lost some information. Now you shift it up 50 backwards, you want to stretch it back out, but then a lot of stuff fell out of the histogram, right? And you lost some information. So it's not always, very simple to just do that and we're done. That's why gradients are much more powerful than looking at intensities. In some applications, the intensities work out pretty good.
In the angle histogram, we said that only the angle, we bin it based on the angles of the change in gradients, right? And doesn't it also need the magnitude as well?
Right, yes. So you also have the magnitude information for you. So you have an angle histogram and a magnitude histogram if you need it. It depends on the feature. Okay? All right. SIFT. The scaling variance feature transform is, I will dare to say, that is the 100% most well-known feature descriptor in the whole entire planet. The paper from 2004 actually suggested in 99, but in 2004 has 43,500 citations. This is, I don't know, if you take like Ari Kaufman here, across all his papers, from all his years, he does not have 43,000 citations, right? I think if you take the whole first floor of professors and you sum all the citations, you may reach 43.5. So this is a single paper. He had other papers on SIFT, and they also have thousands of citations. This idea was so big in computer vision that it basically single-handedly enabled, groundbreaking research in stereo and structure for motion, and navigation. And I would dare to say that without SIFT, or let's say if SIFT was like 5 years later and not in 99, but like in 2009, we would not be thinking about automated driving, automatic cars today. We will still be 10 years out. A very, very, very important idea in computer vision, and you'll get a chance to play around with it a little bit in your next homework. I won't ask you to implement it because I don't think it's a good use of your time. But the idea is that for every key point, you take a histogram of gradients over some sort of a grid. So you have a certain point, and you divide the area around your corner pixel to 16. It's 4 by 4. So this is just 2 by 2, but really in the paper or in the feature, what they do is do it 4 by 4. And for every one of those little patches, you calculate the histogram gradients. You put everything into a big vector, and that's it. That is your feature. You also take care of some overall orientation and scale and so on. We saw how to do it. It's just normalize. If something is rotated at 40 degrees, you rotate back, and then you do your histogram of gradients. If something is, at bigger scale, you normalize the scale, and you take your histogram, and so on, right? And those 128 numbers, floating point numbers, can handle big changes in viewpoint, in intensity. It could be implemented to be very fast. I would also dare to say this is the most implemented feature detector there is, with dozens and dozens of implementations and flavors and other things. These are examples of those SIFTs, those SIFT key points. So in the paper, David Lowe uses a Harris detector. So it was before the FAST came along. So he's using that. But you can actually use it with, well, you can't use it with FAST, but you can use it with other kind of detectors. It's not very particular. The whole idea is that if you know the orientation and the scale for your key point using any kind of descriptor that you choose, you could then calculate the SIFT descriptor. So you can sort of mix and match your detectors and your feature descriptors, right? So as you can see, it sort of conforms with the edges in the image. For example, there's an edge, so the orientation of this feature is like that. There's an edge over there, so the orientation is like that, right? These are sort of the detectors. So SIFT is very, very, very big, very important. Similarly, there were other things like the GLOH, the DLOH, the Graded Location Orientation Histogram. Not a very good name, but it's very similar to SIFT. It only, instead of going in a rectangular grid, just 4x4 grid, they were looking at the polar distribution of the histograms across the thing. It just makes it it is harder to compute. And the HOG, the histogram gradients, that's what you asked, is basically a histogram of gradients across the entire image. And HOG is used, there's again many flavors of HOG, but it's actually used today. It was found to be very good to do people detection, because you can sort of see, and this is the HOG, you can sort of see how it basically creates a grid, and then every grid gives you a histogram of the gradients in that grid. That's it. It tells you every little patch here, 8 by 16 by 16 or something, tells you what the edges are. And it turns out that it's a good feature to describe the silhouette of people. So it ended up a very good people detector. But it's all around the same thing. It's all about histograms of gradients. All right. So the SIFT feature, like we saw, is 128 numbers, of course, a 4x4 grid, and 8 numbers in each histogram, 8 bins in each histogram, and those are floating point numbers. You end up with 512 bytes per key point. So in memory, imagine you have 1,000 key points. You have to keep 500 kilobytes in memory. That's a lot. That's a lot. And a lot of that information can be represented, more efficiently. So what brief, binary, robust, independent elementary features, an orb, is basically rotated brief, they represent it in binary. So instead of using a floating point, they use bits, 0 and 1. Now, remember the FAST, how we did it in FAST? We look if something is bigger, something is smaller. It's a binary decision. So you sort of do the same thing here, but instead of going around a certain pixel, you go in whichever different way. And sort of this pattern is also something that they applied some machine learning, some way of learning what is the best pattern to use, and they came up with this pattern. The idea is that it's sort of like a normal distribution with a little bit more, higher distribution on the inside. It's very fast, because if you have two descriptors that instead of floating point numbers, these are just bit strings, to compare one and the other, remember our goal is to compare one image to another. To compare one and the other, you just do an XOR operation. It's very, very fast in our CPUs. And brief has all kinds of different flavors too, with like 32 bits, 64, 128, whatever. There's even up to 256 bits. There's you can do XOR operation and give you like the score between two descriptors very fast and in parallel. And the oriented fast, these are oriented. This is O-fast. These are oriented fast, so you can see how it finds a key point, but also its direction. Okay, we gotta move on. LVPs, I'm sorry, I won't get to them. They're interesting things and that type of features. There's many other kind of feature descriptors. A whole lot. Brisk, freak, 8Ks, latch. Some of them take longer to compute, some of them take less. The whole idea is that you need to get some invariancy. This is, for example, for rotation. They take a patch and they just rotate it from 0 to 180 degrees, and they compare sift and orb, which is brief, sift and orb, and different kind of features, and whoever is like the highest, wins. And these are different sort of. So we saw how in how we just took sort of a random thing. So they tested in the paper, set up in the readings, some things that are not so random, but these are patterns, sampling patterns of where to sample, that are inspired by the fovea for the human eye, how we look at different key points, and the same goes in here, right? So what people are doing now in sort of feature descriptors and trying to find more, things that will be fast, use machine learning to tune some of the parameters, mimic the human vision, like in Freak, for example, and use binary representations instead of just floating point numbers, because binary is much easier to compare in CPUs, and use the GPU to do some acceleration. So basically, all of the SIFT, all of the usable SIFT detectors now basically run on the GPU. Okay, we don't really have time for questions, so very quickly, like one or two things about some of those descriptors and some of those ideas. Okay, so we'll move on. Right, matching. We have features in one image and feature in another image, and we want to match them. Given features in one image, features in another image, we want to find the matching. This I did with a couple of minutes throwing around some OpenCV code to extract features on this book. I took a picture of my desk with all the books that we use in this class, and you can see how some features here, some of the descriptors, these are SIFT descriptors, they match very nicely in the image. And you can see how even given a lot of occlusion, I put a couple books on top of J.D. Prince's book, a very good book that I told you about. We can still find the object in the image, even though like most of it is included, we can still find it. See how I just put a little marking here, not by hand. I did something that we'll get to in a few classes. To find the object in the image. See how powerful that is? If you get a good descriptor, key point finder, and a feature descriptor, you can find objects in the image even under very heavy occlusion. Right? Pretty cool. Okay? So what do? We match them. We define a metric saying how good is a matching between these two. Let's say we have 128 numbers floating point, another 128 numbers floating point. We can just do an L2 norm, right? This minus that, L2 norm, give you the magnitude of the difference between those two vectors, and we'll tell you if it's 0, then they are exactly the same, right? If it's not 0, it's just a sum of the square differences, right? If something is under a threshold, we pick it up, we do a very greedy thing, right? Simply. We do a very greedy thing. Take the nearest neighbor, the other feature in the other image that is closest to you, and just take that one. That's a big problem, because there's a lot of ambiguity. see how this feature here might match a lot of other features, especially in scenes like this. There's a big problem, and some of them are smaller, true, but since we are scale invariant, they will still match. That's a problem in ambiguity. Features look the same, especially in trains or a fence, something that looks the same, right? So what do? We can take the distance ratio. This is another idea from the SIFT paper from David Lowe. The idea is that you take the distance between one feature. You look at two features in the target image. You have one feature here. You look at the two nearest ones in this image. You take the distance to the first one and the distance to the second one, and just do a ratio between them. Right? What does that mean? So if we have one feature and another feature that's very similar, and we have one feature and another feature in the other image that are very similar, that means that we don't know which one to pick. They're close. The ratio between their distances is very small. The ratio is actually very high. So it will be like, this will be like close to 1. This will be very close to 1. Right? If the distance to 1 and the distance to 2 are almost the same, then we are confused. We don't know which one is actually the best one. So the idea is to remove all of the ambiguities, is to remove all of them. Just not so, if we can't decide for this feature what feature to pick in the other image, we drop this feature. We don't want to be confused by it. It's not that we take the best one or the second one. We drop it altogether. Right? The idea is that if a feature is not unique, it's confusing. Right? So this is the same match that I showed you before without the ratio test. So you see how there's many things that could be confusing. Basically, all the features on the left image are matched to some kind of feature in the right image. One feature or another will be matched. Right? And this, like you saw, is after the ratio test. We were able to get rid of many, many things. Given, a lot or even most of the features in this image are not matched anywhere, because we can't match them uniquely. We have some kind of ambiguity. So we drop them. We only look at the real unique ones. What else can we do? Reciprocacy. We can say, I want all the features that uniquely match between image 1 and image 2, and also uniquely match between image 2 and image 1. Right? It goes both ways. Because if you think about it, it's a little different. You look from each one here, you look at two features here to know if you're ambiguous with the ratio test, what we just saw, and we reject it if you have a higher ratio. But if you look at the feature here, you will find two features in this image, right? We go from 1 to 2 in here, you go from 1 to 2 in here. And we want them both in both ways. We want to keep only the ones that are unique from 1 to 2 and from 2 to 1. And if they align between each other, we take them as a match.
So this is done after doing the ratio test. First we do reciprocity and then
We do two ratio tests. We do one ratio test this way, one ratio test that way, and then we only look at the ones that are feature 70 to 17 and feature 17 to 70. If we have that match, we pick it up, right? Because we don't want to be confused. We really want to do it right. Okay, we only have like a couple more slides, so don't worry about time. We'll finish up very easy, and we'll keep going next class talking about these things. So now we matched a bunch of features. How do we know how good the matching is overall? How do we know how good it is, right? We can look at the true positive versus false positive rate, right? True positive means that we took a feature in one image and we matched it to the right image and the other, to the right feature in the other image. And a false positive will be we took one feature and we matched it to the wrong one. Okay? So the true positives, the number of true positives is the number of detected features that are correct, and the false positives are the number of detected features that are incorrect. Now, we have a control over our threshold, right? If we set a threshold very big, then we'll be picking up a lot of these matches. We'll be enabling a lot of these matches. But we will also probably be letting in a lot of false positives, right? We will probably cover most of our true positives, but we will also be taking in a lot of false positives, right? If we set the threshold very low, we will probably remove most of our false positives, but we will also remove a lot of our true positives. So there is a threshold is like a slider, so you can set it to just the right point where you find, where you can find the highest, and the highest true positive rate and the lowest false positive rate. Okay? So this is sort of our slider, our threshold slider. We can slide it up or down. These are true positives, these are false positives, basically. Right? And since we've got it here, these are true negatives because we just, we correctly said that this is negative. Right? So we can slide that up and down. This gives us the ROC curve, the receiver operator characteristic. Basically, it looks at two statistics, precision and recall. Precision is just the number of true positives over the number of matching features, and recall and precision is just the number of basically the false positive rate. The true positive rate was the false positive rate, and we want to find the threshold that will give us the highest true positive rate and the lowest false positive rate. That's it. Makes sense? I think so. We just need to find that right threshold. Okay. So we don't really have time for questions unless someone wants to keep everyone in class for a few more minutes. But if you have a question, go ahead. Next time we will talk about a little bit more higher models for matching. We'll talk about stitching, registration, and we'll also hand out homework number 2. Thank you.